Okay, good morning, everyone. Welcome to today's seminar. Very pleased to introduce Stephane Randoux from Lille, University of Lille. And he's going to be talking about some really cool experiments he's been doing in nonlinear electrical lines. Please.
Excellent, Prof. Good morning, everyone. First of all, I would like to thank the organizer for the invitation to give this presentation. We will be around next week in 2020, and I'm very happy to have the opportunity to give a talk where I will present you some recent experiments. First, I need to acknowledge many collaborators and contributors to this experiment awards. We will cite everyone. I think that a lot of these people are inside this room. I just would like to mention Louis Fash, who is a PhD student in our group, and the results I'm going to present today are mostly results from his PhD work. Then I would like to mention Hervé Damar, who is an engineer in our group, and he's the guy who did this line that I'm going to talk about. And finally, I would like to also mention Félicien Bonnefort, who is a guy in the north, a colleague in north, who is running this huge water tank facility that we use to do some waterway experiments. So it is an experimental talk. You will see a lot of pictures. You are not supposed to suffer too much, except maybe from the French accent of the speaker. Okay. So, as you know, solitons have been observed something like 2 centuries ago. Since this time, they have been observed in many areas of physics, in hydrodynamics, of course, but also in optics and matter waves and many physical systems. If you are a physicist, you would like to describe a soliton as being nonlinear waves that how is stability due to an exact balance between linear dispersive effect occurring during propagation in the material medium and nonlinear effect. And now, if you are more a mathematician or an applied mathematician, you will maybe prefer to say that a soliton is a particular solution of a certain class of nonlinear dispersive equation, like the NLS equation or also the KdV equation. These equations are integrable, which means that you have an infinite number of conserved quantities during the evolution of the system. And behind this class of equations, there is a particular mathematical structure. This kind of equation results from a compatibility condition between these two lax equations and a hospitality condition. And in this IST formalism, very usually, we parameterize a soliton by one discrete eigenvalue of this lax problem. And this discrete eigenvalue encodes the amplitude and the velocity of the soliton, while the norming constant encodes the phase and position parameter of the soliton. So, for instance, for this fundamental soliton of the focusing NLS equations that you can see there, we have one discrete eigenvalue with the real part being equal to 0, which means that the velocity in the xt plane will be 0, and the imaginary part will encode the amplitude of the soliton. An important properties of soliton is that they collide in an elastic way, which means that soliton will recover their shape, amplitude, and velocities after interaction. And the only phenomenon that will happen during a collision process is a position shift of each of the two solitons due to the collision event. And the amplitude, the magnitude of this position shift is completely parameterized by this, by the eigenvalue parameterizing each of the two solitons. So, believe it or not, this is not a numerical simulation of the focusing NLS equation. This is an experiment that has been done in our group by François Copy using a recirculating Faber loop that I will describe in a few slides. So, this position shift are cumulative effect. So, if instead of taking 2 solitons, you take 3 of them and you produce some collision, the position shift that will be experienced by one soliton is a cumulative shift that would have during collision with the two others, without collision with the two others. Okay, can we now produce some more complicated space-time pattern? The answer is yes. And starting point is IST. So in the IST plane, we talk about focusing analysis equation. In the IST plane, I have decided to put some display eigenvalue at some random position that I selected. And using Darboux transformation method, I go back to physical space where I synthesize this random wave field that I then put in my favorite analysis solver. And you can see that I have a complicated space-time evolution in which eventually solitons cannot be separated. They are always in interaction in this function. They are separated there. And so this is a random ensemble here of only 16 solitons, but it is a good way to introduce at phenomenological level what is a soliton gas. A soliton gas is just a larger statistical ensemble of solitons with random spectral properties. So this concept of soliton gas has been introduced in 1971 by Zakharov. Then it has been generalized by Gennady and some other people later in the around 2000s. In experimental physics, it is only very recently that soliton gases has been observed. First experiment has been made in Grenoble, is a group by Lille, whereas they have this shallow water tank, so water depth is typically 10 centimeters, and they have produced a soliton gas using the process of soliton fission. And this gas is a bidirectional gas because you have some reflection of the soliton at the two edges of the water tank. So you can see typical space-time evolution there, and many solitons crossing each other at many space-time in the space-time zone. Another experiment that we did 1 year later was in École Centrale de Nantes, not in shallow water regime, but in deep water regime, where wave propagation is described by the focusing analysis equation. And
I have a question about this picture, right?
Yeah.
Because it's hard to distinguish whether it's a linear or non-linear thing. I don't see the shift.
Yeah, so the proof, so there is no IST in this experiment. And what they did is fully transform this space-time plot, and you can see that part of the energy is on the linear dispersion curve, and part of the energy is on a straight line, meaning that you have something which is, I would say, you have soliton basically.
I mean, if you're gonna see the shift, there's gotta be a region where they're not interacting, otherwise you won't see the.
Yeah, but you would see some kind of zigzag, right, when they hit each other.
But this shift could be smaller.
We need more drugs.
Okay, so this other experiment that we did in École Centrale de Nantes is more an IST-based experiment. So starting point is IST. We have generated a random ensemble of 128 eigenvalue in this blue square box at some random position. Normally constant are also random. We use our Darboux transformation machinery to synthesize the initial condition, which is used as a signal for the wave maker. And doing that, we can measure the evolution of the soliton gas that I do not show here. And we are also able to measure the density of states of the soliton gas in this experiment. Okay?
Can I make a question? So I showed this picture in front of the optical, and it said, no way you can say that these are solid.
You can see.
No way that you can say that these are solid. And so,
So if you measure your wave field.
So if you measure this later, do you see the same dots? So if you do,
You see dots, but moving a bit under the influence of quickly dissipative effect.
moving a bit.
Moving a bit, yeah.
A bit, how much is this bit?
I can show you later on the plot. So it's not perfect in this experiment, it's not perfectly integrable dynamics, and I will talk more about that later. But roughly speaking, you start with 100 eigenvalue, and you keep this same amount of eigenvalue in the same region of the same spectral domain. So it's more or less something in average integrable, let's say. Again, it is physics.
Yeah. Kind of related question, so the eigenvalues are uniformly distributed in the box.
Yes, at initial condition.
And then how about the norming constants? Are they
They
also
also
random?
distributed randomly. I don't remember exactly how, but I can say.
Okay.
Okay, so this is the experimental realization of soliton gases. So of course it is not integrable. What about theory? I will go fast on this slide because Alex had nearly the same slide yesterday. So central concept in kinetic theory of soliton gases is density of states, already described yesterday by Alex. So typically, density of states is defined very usually as the number of solitons that you find at some time t in some space interval and over some spectral band. So if we talk in simple words, we consider this KDV numerical simulation in which you have a random set of solitons. How would I do if I want to measure density of state of this specific gas? I will take a large space interval containing a large amount of solitons. So let's say this interval between 1,000 and 2,000. I will count the number of solitons that I would find in this space interval in this having this spectral parameter being comprised between mu and mu plus delta mu. And this particular soliton gas, you can see all the solitons are nearly the same amplitude. So we find something which is called a monochromatic soliton gas because all the solitons are nearly the same spectral parameter. And kinetic theory is composed of these two equations. The first one is a so-called continuity equation associated to the isospectrality condition connected to the integrable nature of the wave system that we are dealing with. And the other equation is a so-called equation of states that describes the change of velocities that will be experienced by a tracer soliton when it will propagate inside the soliton gas. This has been explained yesterday by Alex. So if the soliton starts from this position, if there is no gas, so no possible interaction will reach this position. But now if it interacts with the soliton gas, each time that it will collide with one soliton inside the gas, it will acquire some position shift, and at the end it will reach this position, which is something that you can translate into velocity change. And this is described by this equation of states in which the tracer soliton has its free velocity, which is modified by the collision with solitons from the gas. And this, the magnitude of this effect is parameterized by density of state. Okay, so now in experimental physics, we are at the steps where we can go beyond the simple observational evidence of soliton gases in physical systems. We can check quantitatively certain aspects of the kinetic theory. And this is what I'm going to discuss now. So first experiment is an optical fiber experiment that we did in Lille. I'm going to describe the experimental result first, and then I will explain how we got this result. So the experiment is consists in colliding, let's say, a single tracer soliton and a soliton gas. So the initial soliton, so the typical duration of this soliton we are in optics is 50 picoseconds typically. It has zero velocity, and it will collide with a soliton gas that you can see there, that has an extension of 2 nanoseconds. The two objects collide, and you can clearly see on this inset that as a result of the interaction between the tracer soliton and the soliton gas, you have a change in velocity of the tracer soliton. So this is very similar at qualitative level to what you observe in ray optic when light ray goes through a piece of glass. You have reflection phenomenon. This is similar to that, except that here we talk about nonlinear waves. Okay, so this is very nice experimental result. How did we get that in our optical fiber experiment? The starting point of the experiment is preparing the initial conditions. So we have two lasers with two slightly different wavelengths. One of them is producing the short pulses. The other one is producing square pulses, which are perturbed by small noise, and this develops into modulation instability. And you can see this random evolution due just to the amplification of noise in the system. So these two objects are combined using this coupler and reach this other coupler. Part of the light is going to photodiode and oscilloscope for detection. I can see my initial condition. And part of the light is going inside the fiber loop, and I can reach the coupler again. At this point, part of the light is going to photodiode. I can observe what has happened after 8 kilometers of propagation. And part of the light stays inside the loop, and I can see again what happened after 16 kilometers of propagation. And I can do that many times. Of course, I have to have in mind that each time that I reach this coupler, I lose 10% of energy, so I need to compensate the losses. And for doing that, I use a process of optical amplification using some random counting. So at the end of the story, the light power inside the receptacle fiber loop is not perfectly constant. There is a small dissipation. We lose 50% of power and over a propagation distance of 1,060 kilometers. So this 1,060 kilometers that you can see there correspond to normalized evolution time of such. Now we can reach something like 100 with better experiments. Okay, all that is well described by the focusing analysis equation with the small damping terms that you can see there. So we didn't do only one experiment, but several experiments changing the size of the soliton gas from small size to large size. And we can measure the position shift experienced by the tracer soliton and compare the value of this shift with the result from the IST theory. As I said before, the shift is a cumulative effect. So it is the sum of many individual shifts between the tracer soliton and all the soliton composite the gas. And as you can see here, on this plot showing the value of the shift as a function of, let's say, the number of soliton inside the soliton gas, we have very nice agreement between experiment and the IST theory. Now,
This is the dilute case, right? The theory that you're comparing to is the
IST. We just considering that the continuous part of the spectrum does not play any role. So we compare the experimental shift with this shift that you can get from IST.
And you compute the spectrum from the initial.
And we so this experiment we do not compute IST spectrum, but we start to be able to do that. So this is a box. So we measure the amplitude, the width of the box, and if we assume that this measurement is correct, then we have the distribution of the value. This is the direct measurement of the IST spectrum, but this is inferred from the.
I got confused, sorry, so this is not the speed, you're between the shifts.
This is the shift.
Okay, sorry.
Now it is the speed. So now we use the perspective of kinetic theory. The perspective of kinetic theory is okay. Let's put ourselves in our another reference frame, the one of the soliton gas. But now at zero velocity. My tracer soliton has now a velocity. In the experiment, this velocity is 4.7. And you can see that it is refracted by the soliton gas. The velocity changes, and it changes from 4.7 to 5.2. And this is in agreement with prediction with the kinetic theory. If we assume that we know the density of states, and we do the density of state because we start from a box, and the density of state for a box is this very distribution that that Alex was discussing yesterday.
Which is not dilute.
Yeah, that's dense gas. So this is, if you want, in some region of parameter, a quantitative check of the validity of the equation of state. Because the evolution is not integrable because you have small dissipation, but we check that the equation of state is correct for dense gas. Okay, another experiment in which we are able to do quantitative checking of the kinetic theory starts from a paper by Binadi in 2005. So we have kinetic theory, but for focusing LLS. And as you know, these equations are complicated. It is an integral differential equation, but it happens that they simplify a lot if you use this on that, in which you specify that you can only have two species of soliton gases. The one parameterized by parameter lambda 1 and the other one parameterized by parameter lambda 2. And if you plug this and that into these two equations, things simplify a lot. I'm not going into detail, but I'm sure that Binadi will be happy to explain this more into detail. At the end of the story, we have some formula for describing the change in velocity and density of the two gases. And this you can understand on these numerical plots. So this is my two eigenvalues, lambda 1 and lambda 2. And the general part is 1. P part is minus 0.5 plus 0.5, which means that I will have two species with opposite velocity. Yes.
Sorry for interrupting.
Yeah.
In the previous slide.
Yeah.
How many different speeds did you use for the tracer solid?
Just one because of experimental limitation. And this speed is relatively fast. And it will be interesting to change it to smaller velocity to see if we, okay. Okay, so we have two monochromatic soliton gases with these two eigenvalues. initial condition is these two boxes. So first species is at this position with uniform density. Other species is at this other position with uniform density. And these two soliton gases will collide, and the result of the collision is a drop into the density. And also a change in velocity that you can see here, similar to the refraction phenomenon that we've seen before. Okay, so this is a numerical simulation of kinetic equations. So this is abstract theory. Now we need to move to physical world, and the first good step is to do numerical simulation. So this is numerical simulation associated to simulation of kinetic equations that I showed before. So starting point is, as usual, IST. So we design each of the two gases by taking two narrow clouds. Each cloud contains 50 eigenvalues, a bit at random position, and all of them have random normal constant. So this is my two spaces. I use my Darboux transformation method to synthesize the soliton gases, and this is my initial condition under the form of two soliton train. All these soliton gases are monochromatic, which means that each soliton in one given species has nearly the same amplitude as its neighbor, nearly the same velocity, and randomness can be appreciated by a small random difference into the distance between two neighboring solitons. You can see that. But you can compute the density of the initial state just by measuring the number of solitons that you have per unit of length. You can do this in the interacting region and in the region where there is no interaction, and that's fine. Okay, so this is numerical simulation. We are fine with that. Look, the normalized evolution time is 140. This is a lot. So we need to go to an experiment, and so this is not realistic for a physical experiment. You need to maintain an integrable nature of the wave system over this evolution time. This is huge. Okay. So we did the experiment in using this water wave tank in École Centrale de Nantes in France. So the water tank is 140 meters long. The width of the tank is 5 meters, and water depth is 3 meters. And you can see here a typical soliton that we are able to generate. So this is typical orders of magnitude. So the period of the carrier wave is typically 1 second, which is associated to a wavelength of 1 meter. You can see here this small oscillation is just your carrier wave that you can see by eye. Of course, the orders of magnitude are very different from a typical fiber experiment. And typical extension of a soliton is, let's say, 5 to 10 meters. And the amplitude of the soliton is a few centimeters. Okay. So this is, I forgot to mention that we measure the wave field at 20 different positions along the water tank by putting some resistive gauges, 1 every 6 meters, and doing that, we can recompose the space-time evolution of the wave field. So this is an experimental space-time diagram. So you cannot see this cross that you saw before in the numerical simulation because we don't have this large evolution time. We just have a small evolution time. It is not written normalized unit, but here it is something like 5. Okay, but the solitons that you see here have no interaction with others. It is first species. The solitons that you see here have no interaction with the others. It is second species, and this region is the interaction region in which soliton interacts. And we can measure, so we can measure IST spectrum because we can measure the wave field. So this is our initial IST spectrum. This is now cloud that I was talking about before. And these red dots show you the IST spectrum measured at the end of the tank. So you can see that isospectrality condition is not fulfilled, but it is experimental physics. Still, we keep two narrow clouds that decay a bit because of small dissipation in the experiment. And so we can measure densities of the soliton in the interaction region just by counting the number of solitons that we have per unit of length. So this plot here shows you the densities as a function of the interaction strength. So just the relative velocity between the two solitons.
I mean, but the change is a lot. It's from around to 0. So you consider this small. I mean, that's to understand the scale.
Yeah, and why I consider small because I compare the agreement between my experimental result and kinetic theory. And so this plot that you can see there is evolution of densities of one given species as a function of the relative velocity between the two species. And the green points that you see there are my experimental measurement, and this black line is a result from kinetic theory, where you suppose that you have integral integrity that is preserved. And okay, I will go to this question at the end of my talk. As experimentalist, physics is not integrable, but integrability is nice basis to try to understand physics. So I accept this, and
I would say.
yeah, I accept this because I can. So this means that kinetic theory integrability is relevant to my experiment, even so it is not integrable, because all that is consistent and providing some insight into the physics of our system.
The laws if they are constant, so they
Yeah.
don't change.
Yeah.
Yeah.
Could you say again what the plot is?
So the plot is density of one given species in the interaction region as a function of the relative velocity between the two species. So I changed the real part of the value.
is the relative.
Yeah. And so if I go to small relative velocities, then the strength of the interaction is increasing because the soliton try to interact more, and the density change is stronger.
Sorry, okay. How do you measure the density of one of the species? when they interact?
Just by in interaction, because they go in one direction, so you can use some filtering process to keep on them.
You can identify the ones moving to the right.
Yeah. So this is quantitative. This experiment is quantitative experimental checking of the validity of Guinadis paper in 2005, and it works well in the experimental regime of parameters that we are able to check. Okay, now let me go to the most recent experiment, not done in water wave or optical fiber experiment, but with this elliptical line. And let me start with something that you learned at school. When you have considered a mechanical chain of oscillator composed of mass m and springs, and you assume that Hooke's law is valid in such a way that the relation between the strain and elongation is linear. If you do that and apply Newton's law to one of these oscillators, you end up with this second order differential equation telling you that the motion of one given oscillator is coupled to the motion of the two neighbors. And if you have a huge number of oscillators, the usual way is to go to continuous limit. So I skip many details that you can find in a nice textbook. At the end of the story, if the oscillators are linear, you end up with this propagation equation in which eventually you have some dispersive theory. So that is this system. Now, if instead of having a linear oscillator, you have a weakly nonlinear oscillator in which the relation between the strain and elongation is no longer linear, but given by this thing, you can apply the same treatment. You end up with this new second order differential equation, and you can apply the same treatment. And at the end of the story, I skip many details once again, but you can find in the textbook. You end up with the idea that the wave propagation in this nonlinear chain of oscillator is governed at leading order by KDV equation. So very nice. You can imagine doing that in an electrical system instead of a mechanical system. And now instead of having a mechanical oscillator, you can have electrical oscillator composed of inductance L and capacitance C. This capacitance is not constant. It is a nonlinear devices. The capacitance is a nonlinear function of the voltage, a linear function of the voltage. It depends on the voltage. And this is analogous to the mechanical chain that we just saw before. Instead of applying Newton's law, you apply Kirchhoff's law. You end up with a differential equation. You perform the same treatment at leading order. Wave propagation in this electrical line is described by KDV equation.
The fact that the capacitance is a nonlinear function, it's a well-known fact in.
Yeah, so this is in textbook, and if you have some relation like this, you end up with KDV.
Yeah, I'm okay. No, I'm just asking about the physics.
Yeah.
The fact that the capacitance is nonlinear.
No, most of the capacitance that you can buy are designed to be linear. So, of course, the capacitance will always depend on voltage.
Yeah.
If you go to 1000 volt, at some point, the capacitance is no longer linear. But these components that we use are specifically designed to have this kind of response to the voltage.
Okay.
So this is not constant. It is designed to have this needle.
Okay, you can buy these.
And this is what we did. And this is the electrical line that we did in our lab. So this has been done by Hervé Damar. So each of these small points that you see there is this nonlinear capacitance, and behind the plate you have inductors. So there is an ensemble of 160 oscillators connected like this, like a snake. We can plug any arbitrary waveform generators that you can find in the labs, just standard devices, and you can measure the voltage at each of these LC cells all along the propagation. And the first experiment that we did is propagation of one soliton. So this is the raw experimental data. This is the cell index from 1 to 160, and this is time. And initial condition is a Sech square pulse, KDV soliton, if you prefer. And you can see that we have a very nice propagation of the soliton inside the system. If you look carefully, you will see that the amplitude of the soliton decays a bit. You can see there, but at the same time, the width of the soliton increases. In such a way that the product of the amplitude by the width to the power of 2 is constant, which means that you have adiabatic evolution of the soliton in the electrical line. Which means also that you don't have pure KDV evolution in the system. You don't have pure KDV evolution in the system because these nonlinear components are not purely capacitive devices. They are also a bit resistive. So you have a bit of resistance in these devices. And this results into the fact that at the end of the story, wave propagation is not governed by KDV equation, but by KDV Burger's equation, with the Burger's term being relatively small. So to check that, we did other experiments. So this is an experiment of soliton fission. So instead of starting with a fundamental soliton, we start from a box. And here on this plot, you can see soliton fission. And there are two curves in perfect agreement, here perfect agreement, showing a numerical simulation of the KDV Burger's equation and the experimental result all together. Also, you can make some other experiments like overtaking collision, and all that you have nearly very good quantitative agreement between experiment and numerical simulation of this KDV Burger's equation.
The overall resistance of the circuit is not relevant.
No, it's not. So inductors have a very small resistance, 0.06 ohms. This is negligible, and I don't really understand why the resistance of these varactors, we call it, is so large. In the data sheet, it is supposed to be 10 times less than it is now. Okay, so there is no damping. In other words, there is just diffusion, no damping.
That's meaning that this resistance of the varactors does not
Does not damp.
not
Not damp, just produce this effect.
Are you getting the Burger's phenomenologically, or are you getting it from the Kirchhoff equations?
You get it from Kirchhoff equation. So now that we are at this step, we can think about taking soliton gas as initial condition in our experiment. So this is what we did. Starting point is usual one. So we start from the IST. We have specified an ensemble of 200 discrete eigenvalues comprised between 0.2 and 0.6. Normally, position parameters are also random, CBV. And eigenvalues are randomly distributed over this spectral interval. And using my Darboux transformation machinery, I can synthesize soliton gases. It is a dense soliton gases that you can see there. With this fluctuation that you can see on the top, no soliton can be individualized. And we use that as initial condition in our electrical line. And as you can see, as a result of the evolution, we have this dynamics. So at short time, diffusion plays the role of smoothing the oscillation, but at longer time, you have the emergence of this asymmetric wave field that you can interpret as being a rarefaction wave, which is connected at the leading edge to a diffusing dispersive shock wave. This has been emergently identified by the idea of the dispersive diffusing shock wave. This is what our experiment reveals in terms of space-time dynamics. When we go beyond that, we can go beyond that using IST. So, auxiliary problem associated to KDV is Schrödinger problem. So what we did is solving numerically this problem for the wave field that we measure in our experiment. So this plays the role of potential in nonlinear Schrödinger equation, in linear Schrödinger equation, sorry. And we can solve this problem. Yeah.
Sorry, it's a background question.
Yeah.
This, in mapping from the circuit to the KDV equation.
Yeah.
What is the spatial variable X? Does it correspond to kind of distance along the?
No,
along the circuit?
Where can we go?
This last box.
This one is here. So this is cell index. So the point at which I do the measurement, which is evolution time. So this I will convert into time. So the position at which I will do the measurement will be time, and the physical time that I measure on my oscilloscope is space. So the time at which I measure the soliton is the position of the soliton.
So is it, okay, okay. It's time is discrete.
So the time is continuous because
It's this.
this time is discrete, but we don't see the discreteness because we are in one wavelength state.
Okay, thank you.
So okay, we have this nonlinear evolution in physical space, and we want to learn more about that using IST. So the auxiliary problem associated to the KDV equation is a linear Schrödinger problem, where the wave field that you measure plays the role of a potential. So if you analyze our initial condition by solving this linear problem with our initial condition being the potential, you can determine discrete eigenvalue, and you will find our 200 discrete eigenvalues that we have specified as initial condition. That's okay. Now, dynamics is not isospectral at all, because we have these Berger terms, and if we solve the same Schrödinger problem at long evolution time, we will see that the number of eigenvalue has increased a lot. It has increased from 200 to 225. Isospectrality property is not fulfilled at all. And also the spectrum has changed. So we started from this spectral support and we go to this other spectral support. Okay, because of this term. And now if I look at the evolution of the eigenvalues of the function of time, I have my initial eigenvalue between 0.2 and 0.6, forming this black flow that decay a bit. And we have another flow of new eigenvalue created during the evolution and starting from 0. So the 200 eigenvalues that are specified initially evolved according to this flow, and the new created one, the newly created one, evolved according to this new flow. I look at your face and see it is complicated, so let's simplify. Simplify by
They're all born at 0. All the new ones come out initially.
very quickly, not exactly at 0, but very quickly. So let's simplify and take another simpler initial condition. Let's take a soliton as initial condition. So we see in the elliptical line the evolution of a soliton as a function of normalized time. So because of diffusion, the amplitude of the soliton does not remain constant, it decay a bit, and as a result, the velocity also decay a bit, which explains this curved shape that you see there. But if you look carefully, you have also formation of something behind the soliton that you can see better here, and this thing is named a shelf. So we have a shelf emerging behind the soliton, and all these features are very much reminiscent from what happened in the propagation of soliton in KDV with slowly varying bathymetry. So if you take a canal with slowly varying bathymetry, you will have exactly the same feature. And all this has been studied a lot in the 70s, 80s. Now, if you take our IST perspective of this evolution, what you see is that the initial eigenvalues that you specify decay slowly, but you have creation of two new discrete eigenvalues. Okay. Yeah.
Maybe a stupid question, but is it possible to have eigenvalue destroyed?
Not in this system, but in NLS, when you put some damping, you can have some eigenvalue destroyed.
Assuming the red solid line, it's a fit or it's.
No, it's numerical simulation of the experiment. So we do the same, but in numerical simulation, of course, you don't have any noise, and you can compute the spectrum at different evolution time, and you have this red line. So this proves that the experiment is very well described as the equation. You can think about the equation and forget the Okay, so let's try to better understand that. And let's go to numerical simulation. So this is the same as before, but the evolution time is 100. And it was 15 in the experiment. We see the same kind of evolution. And I must emphasize that an important property of the KdV-Burgers equation is that the mass must be conserved. Mass is defined as L1 norm. It has this expression, mathematical expression. So it is conserved quantity in KdV-Burgers. Contrary to momentum or energy that are not conserved. And also you have this expression of the mass from the IST. And you have a contribution to the mass from the discrete part of the spectrum and the contribution of the mass from the continuous part of the spectrum. That okay? So let's move on. These other plots show you here the fact that in numerical simulation, mass is conserved, not momentum, not energy. This shows you the evolution of my discrete eigenvalues. The first one that I specified decay in time, and you have creation of 4 new eigenvalues. That's okay. Now I compute what I will call the discrete mass, just as the sum of 4 times the sum of each of my discrete eigenvalues. What I get out so that is this black line that you can see there, just above the dashed line, which represents the conserved mass. And what does it mean? We learn a lot from that. We learn that due to the fact that we have diffusion in our system, the amplitude of my initial eigenvalue decays in time. So this means that the mass is decaying in the system. And the system has no other choice to produce another eigenvalue to compensate for this loss of mass. And this explains this small bump that you observe. But if you just call the discrete part of the spectrum for doing that, you never compensate exactly. So you need to for having perfect compensation of the mass, you need to have opposite oscillation of the mass of the continuous part of the spectrum. So in these dynamics, you have opposite oscillation of the mass of the discrete spectrum and the mass of the continuous part of the spectrum in such a way that the total mass is conserved. Yeah.
Is it possible to write an evolution equation for the spectral data?
And the answer is
Next slide.
the next slide, and the answer is probably difficult because what we are dealing with now is named nonadiabatic effect. All what we are dealing with cannot be tackled by using a perturbative IST because you have creation of new poles during the evolution. You have excitation of the continuous part of the spectrum and creation of new poles out of that. So things are relatively simple when you just have one solitary wave. They become much more complicated when you have this initial soliton gas. And when you look at papers from the 70s, 80s, you don't have much about that because it is nonadiabatic features. Okay, nevertheless, let's try to do more. And let's go back to IST. So as I said before, the auxiliary problem associated to KdV is a Schrödinger problem. And when I take a soliton as initial condition, very often what I will compute is just the discrete eigenvalue associated to this soliton. So for the soliton, the eigenvalue is 1. And I will forget to compute the associated eigenfunction, this phi1. And if I just have one soliton, this associated eigenfunction is Sesh-like. Okay, you are. Now, if instead of taking a fundamental soliton, I take some solution which has Bishop soliton content, so this formula, I solve this problem for this potential, and I will get three discrete eigenvalues, 1, 2, 3. And if you look at the associated eigenfunction, the first one is Sesh-like, but the others are not. Now, question for you. If instead of taking Sesh pulses, I take a box, how are the solitons inside the box? I'll simplify everything. I'll give you 5 seconds. You must answer. So the answer is that. What is a soliton inside the box? Just oscillatory function. And of course, you do that because you have learned quantum mechanics at school. We are dealing with a box potential inside the Schrödinger equation. And the eigenfunctions look like this. So the eigenvalues are distributed according to what is called Bohr-Sommerfeld law. And the period of oscillation is small for largest eigenvalue and largest for smaller eigenvalues. So this is nice.
So I want to like
I'm plotting the eigenvalue plus the eigenfunction. So this representation is nice because you can see at the same time eigenvalues, yeah, and eigenfunction that you get from the same. The eigenfunction associated that you get when you solve it. Okay. Okay. It's the same. It's just another potential, Sesh-like. And you have 3 eigenfunctions and 3 discrete eigenvalues. Is that okay? The message is that a soliton, when you have some interaction, something dense, has not a Sesh-like shape. Okay? So let's go to soliton gases. So this is not the soliton gas that we have used as initial condition in our experiment, but I can apply the same treatment. I can compute the discrete eigenvalues and also the associated eigenfunction. What I see is just something which is messy, just something random. But the very nice point is this following one, is that using all these eigenvalues and all these eigenfunctions, you can recover the initial conditions that you have specified just by using this formula, which involves square eigenfunction. So the initial field is just the summation over the squared eigenfunction with appropriate weight, which is just the eigenvalues that you have. So this is something maybe forgotten in the IST, because when you do the inverse, people talk to you about Gelfand, Leviton, Marchenko, or some Riemann-Hilbert things, but this is very nice formula that you can find in very old IST paper, and you just have a simple combination of eigenfunctions and define your field. Maybe trace formula. Okay. Thank you. Let's have a look at our soliton gas. So this is the one that we used as initial condition in our experiment, noisy pulse. And I do this treatment. There is 200 eigenvalues in this thing between 0.2 and 0.6. I have some random eigenfunction that I can plot, no problem. And now I put, instead of putting that in my KdV burger solvers, I put that in my KdV solver. And I look at what happens. What will happen is that this propagate, and I will have a round ordered train of solitons. The largest one at the largest velocity, I get it there, and the smaller one at smaller velocity, I get them there. And now, if I look in terms of the evolution of the eigenfunction, I have something really striking, because I see that the evolution is isospectral. The eigenvalue remain confined between 0.2 and 0.6, of course. But the evolution in KdV is such that these eigenvalues that were delocalized in space becomes localized in space under the form of Sesh pulses.
The eigenfunction.
The eigenfunction, sorry. Okay.
So what was the statement?
So I start from that, which is a mess on the soliton gas. Okay. Eigenfunctions are delocalized, more or less, in space. And under the KdV evolution, I reach this soliton train associated to the fact that the eigenfunction become localized. Now, what happens if I turn on the diffusion term? The story is completely different, very striking. So we start from the same initial condition. We have KdV Burger's evolution now. We reach this rarefaction wave connected to the dispersive diffusion waves that we are talking about before. And if you look to the eigenfunction, it is no longer localized peak, but completely delocalized eigenfunctions that nearly have the same oscillatory state, and all that is completely delocalized in space. So in terms of evolution of the eigenfunction, we have creation of new eigenvalue, but also complete delocalization of the eigenfunction.
They seem to sync also the eigenfunctions. They seem to have the same frequency, or is just a physical, visual.
Honestly, I don't know. I think it's more or less the same frequency, but maybe it can change. I don't know. Okay, now if we take some, so it was for the slide before was for dissipation equal to 0. This one is for relatively strong dissipation, 0.1. This is what happened for dissipation being small, but non-zero. And you have something in between the two results before. You have formation of a broader dispersive diffusive shock wave, and part of the wave functions become delocalized, and part of them are part of them become localized, and part of them becomes completely delocalized.
Sorry, could you maybe you're understanding that? Can we see on this plot how the creation of eigenvalue manifests?
Yeah, you can see it there because initially you don't have any discrete eigenvalue in this range between 0 and 0.2, and here you have new discrete eigenvalue between 0 and 0.2.
Maybe I missed it, but with the Burger's term, which eigenfunction, with the eigenfunction of which spectral problem are we plotting?
The same as before, so the Schrödinger problem that I solve, forgetting that I have some dissipation.
Ah, okay.
Okay, because it's like I have a nonlinear system. I will use Fourier transform to analyze my wave field. I have a non-integrable system, and but perturbation is small.
Yeah.
I solve it as if it was integrable.
Strictly speaking, if you say you're in the wrong basis for that new problem.
Yeah. So I use IST basis to analyze my wave field.
Of KdV.
Of KdV, which is relevant at physical level. As physicists, I need a basis to try to understand what happened in my physical system. So either it is Fourier basis and you have a noisy pulse that you filter noise, either you use IST and you have something else. Okay.
Stephane, there is a strange effect. It seems that for small epsilon, the range of energies is shrunk.
I don't know why.
Okay.
Just variations. Okay, so this slide here summarizes everything that we saw before. Okay, and let's make the last interesting step. So this is the IST formula that we price formula that we discovered from one paper from IST, telling you that if I have an n soliton solution, then the field is just the summation over the square eigenfunction with the weight being given by the eigenvalue. Okay. Now we look at the kinetic theory of soliton gases. It tells you something very simple. It tells you that the mean value of your field is just some simple integral over the density of states. And if you look at these two formulas, they are very, very similar. And this provides you a way to compute density of states. Density of states is just the statistical average over your square eigenfunction. So we talk about measuring the IST not as before, just by counting the number of solitons in a given spectral range, but now by using my square eigenfunction and averaging over there. So the last thing that you need to do is doing some statistical averaging. So instead of doing one experiment like this, you do many realizations with the same initial distribution. And if you do this, you end up with this plot that represents the density of set. I will move to the other one, it will be more clear for the audience. So this one is the density of state of my initial conditions. It tells you that in this region of space, you have a large number of solitons with this spectral parameter, but in this region of space, you do not have this large solitons. if you go to the KDV dynamics, you have this density of states being changed into these simple lines, which is associated to the fact that solitons separate from each other. And if we look at what happened in our experiments, density of states look like this. So it has changed a lot from this to this. And if you look at density of state at a given space position, so I just made a cut of this, a slice of this curve, you will see this blue point here that are very well fitted by the Veil distribution. So this tells you that in my experiment, if I use the IST perspective, I have the formation of a condensate. So I start from something which is dense but not condensate, and I go to something which is condensate by the process of reorganization in space of the associated wave function.
Sorry, that's the Weil law for what potential? That's the Weil law for what potential?
Yeah,
The box.
about.
Corresponds to the, I mean, this is corresponds to the law for the box.
The box came from the beginning of the
No,
experiment.
there was no.
There was box, okay.
This is the result.
Yeah, it is that.
Everything, the system gets reorganized, so as if it is a box.
I see, okay.
Just want to comment that, so what this suggests, right, that this, the condensate seems to be a natural relaxation point of the system, which ties up very well with Alex was saying, right, the minimal energy of the
Yeah.
condensate.
You can say it as it, but again, I will say that in KDV Burgers dynamics, you have some attractor physics, and you end up with this dispersive diffusive point, whatever you start with.
Yeah, I can't tell, but if I took a vertical slice at the
Yeah.
initial condition in the middle, it might also be a Weil distribution.
It is not. I cannot show it now, but it is not. It's absolutely not.
It's got the same shape.
Yeah, but it's not. The only requirement that you must have is that initially you start from something which is dense. Dense enough.
So for you, a condensate means exactly that
Yeah,
distribution.
yeah. Because it is associated with the fact that this sigma in the kinetic theory is equal to 0, and also the entropy of the system is 0, and fluctuation in the system are also 0. It's associated all to the kinetic theory framework. And if you look at the other one in which the dissipation was much smaller than in the experiment, then you see that the density of states is not exactly the same. If we do this slice of this position in space, then you have the density of state that lives on two bands. So it is in kinetic theory, it is specified as a genus 1 soliton gas. Condensate, sorry. And you can fit very well what we have in experiment by this formula that you have from the spectral kinetic theory of
Is that also from your point of view, the only density that would be a soliton condensate of genus 1 up to shifts of the lambdas?
Yeah. It is a point view of spectral kinetic theory.
It's a unique solution of this NDR in the condensate case, so it's more unique.
Okay. So the point here is that if the system is integrable, if you want to observe condensate, you have to prepare the system in this initial condensate that it will stay just for a short time in this condensate state in KDV dynamics. Now we start from something initially dense, and we end up with formation of a condensate. This is a point due to dissipation. Well, I think that I reached conclusion. So we saw some experiment. So experimental world is not integrable. So you have to deal with that. But IST and kinetic theory gives you a very nice basis to analyze the experiment. You have to deal with that and to find your way into that and do reasonable things with that. So if you look at the water wave experiment, isospectrality condition, according to Tamara, is not fulfilled at all. But for me, as physicist, the kinetic theory provides me some very nice result because it gives me some prediction of the evolution of density of my gas that I can check with my
That's the
experiment.
definition of what is mode.
Yeah. That's okay. This is physics. What is physics? So for me, this is nice. okay, this is not isospectral, but I am fine with that because, that is nice. If I look at the soliton refraction experiment, I don't know if you can see it well, but if you look carefully, the velocity of the trisor soliton after the interaction is not zero. That's changed a bit, which means that the interaction in the experiment are not perfectly elastic. But if I look at these points, I'm fine as a physicist. Okay, there is good agreement. I measure a shift. This is an agreement with something deep, which is IST. So okay. Now this experiment is very nice because what? Dissipation is small, perturbative, but it brings you something completely unexpected, which is mathematical construction from the perspective of physicists, which is a condensate. And here I have experimental realization of the condensate due to this small perturbation. So the formation of this condensate cannot be described as this kinetic equation because integrability is a prerequisite. So you need integrability sorry. The formation of this condensate is a fundamentally nonadiabatic process that cannot be described as this kinetic theory because they rely on the integrable nature of the system evolution. But here, so the message for mathematician, applied mathematician, is that it is interesting to probably to investigate this non-adiabatic future and to try to find some correction to that to better understand why this kind of object emerge in our physical experiment. So that's it. Thank you for your attention.
From the audience, come up in the back. You give a chance.
That's why I said front is like
Pounding here.
So in this final thing with the Berger's term, you're saying it's a nice way to actually, the final state of it is a nice way to prepare an initial state for then something purely integrable.
Yeah, so this is some if you reach this state, then you can think about putting this as initial condition in a system in which physics is described not by KdV burgers but by KdV, then you will produce some Joule expansion.
Yeah.
So all the solitons that are in the condensate state will expand due to the fact that they are no longer trapped in this condensate state.
So you need better capacity.
This is the point.
In a simpler experiment where you had the single soliton creating the shelf, did I understand it correctly that basically the interpretation is that the shelf at the level of your IST is basically the formation of these additional eigenvalues?
Exactly.
But then what is kind of the intuition? Because the additional eigenvalues at the IST level are additional solitons, but this is not additional solitons, it's a shelf.
It's additional soliton of a smaller amplitude and larger extension. You can see it like this. Or you can also
So many, like a few broad solitons should be interpreted.
Or maybe better point of view would be to do this nonlinear spectral analysis in which you compute the associated eigenfunction to these two.
Right, I think that would be useful, understanding this effect, because as you said, there were these old works by Mark and Yuji and so on that were doing this, so it would be interesting to compare with that.
Well, thank you for the talk. So I'm just wondering if there are other quantities that could be predicted theoretically or measured experimentally besides, phase shifts of solitons. Like, could you do the PDF of the field?
Yeah,
Is there a prediction for that?
Pierre can talk a lot about that. In optical fiber experiment, we can measure PDF of the intensity, so the radius square of psi.
Is there a theory that makes a prediction?
No, Pierre will be happy to say more about that.
There are a lot of results in nonlinear Schrödinger equation from the community of generalized hydrodynamics.
What about KdV?
So I want to come back to my question. So when you have these epsilon in the KdV burgers, is there an expectation that the dynamics is continuous as epsilon goes to zero, or it destroys immediately the dynamics of the spectrum?
If immediately you have epsilon bigger than zero, then you have this future that you can.
Right, they want to
doesn't
think
look
of
like
what
it's
happens if
spontaneous.
epsilon goes to zero.
It doesn't look like it.
It doesn't look like it's an
Yeah.
immediate destruction of the isospectral. So maybe that one can study some kind of analytically, right? Some evolution of the spectrum in the limit epsilon goes to zero plus. If it's non-trivial limited to that.
There is one paper in 1980s, which that describes the growth of one discrete eigenvalue when epsilon is small. And you check this, and maybe you are wrong, but the formula is not correct. But the approach is correct. It is, yeah.
I have a question about the last slide. You were explaining that this limiting state is something adiabatic. And so there's two sets of eigenvalues. There's the dynamics of the existing eigenvalues, and there's the birth of new eigenvalues. Is it clear which one of those two is responsible for the formation of this limiting state?
I would say it is collective thing. So I think that all the system reorganizes itself to produce what we see in the physical space. So I do not think that I don't know, but I don't think that these eigenvalues are completely independent from these new ones.
But the number is much less, right? You're only forming
Yeah,
a small number.
If you look at the eigenfunctions, deep change. There is a big reorganization of the eigenfunction in the system. So this is a huge collective effect that's important.
So I don't think I understand your answer about the last slide. I don't understand the way of genus one. So what did you get? Yes, yes. So what is the statement? Yes, of this genus one stuff. When do you get it?
So we start from the same initial condition as usual. Diffusion is much smaller, and we got finite time, the same as was the other simulation. And we observe that the density of state does not take the same shape as with the experiment. And if we look at the density of state in this position in space, we just observe that we have this genus one condensate.
Yes, what is it? So the picture there is the picture with the picture. What is the picture?
This one, density of state. The density of state that we measure according to what I explained before, using this price formula and those things.
Now the physical, sorry, the physical evolution, so the physical space. How is it?
This one. So you just have a border dispersive diffusive shock wave.
Sorry.
All right, how about we wrap up the lively discussion? Thank you for watching.